Yeah.
Hi everyone, welcome to the data structures and algorithm session 5 of 1, session 5 and session 5's first part. So what has happened, we have announced to start with that there will be 7 sessions of data structures and algorithms. This was after the covering of the fundamentals of computer science followed by the C sessions. There are some dozen, 10, 7 to 10 sessions probably for C. Now here it is, uh, I don't know what to call session here because we have been dividing based on the data structures and algorithms. So the first session was data structure and algorithm, followed the second one was on the uh, so
Linked
what
list
is
stuff.
Huh? Yeah, linked list. Second was on the linked list. So that time is what we took the decision to divide it because it became a very longer session. So to reduce the session size, we said we section it. So session one we put into list, linked list into 3 parts: linked list, the doubly linked list, and circular. And then we had one example, and then we followed that with stacks and queues in one session, then sets. And after sets, we did the hash table 1, hash table 2, and then we are now into the tree structure. So data structure for tree is what is today's topic. This also has a session 1 and 2. Session 1 will focus on the fundamentals, mainly on the tree and the binary tree structure and binary search, etc. And later on, we will follow up with other examples and all. So with that, I will hand over to our study circle lead who has been leading for various presentations. So Jaimit Wasawa, who has been contributing to this meetup and PG Diploma AI Data Structure and Algorithm course for CDAC and any other uh, organization. It could be used for even what you call JE and all that. So with that, I will hand over to our expert, Jaimit Wasawa. Jaimit, go ahead. We have audience to listen to and to comment and get your get feedback for you. Thank you.
So, hello everyone. First of all, thanks, Preorder, for the introduction. And welcome everyone for the data structures and algorithm session 5.1. So, today we'll be covering trees. Previous to this, we have covered the hash tables. So, let's get started with the trees. So, uh, going to the basics, this is what a tree structure looks like in the image. Uh, uh, First of all, we start with the nodes. What does a node mean? It's a single element in the list, and depending on its relationship with different, we can call it with parent node, child node, and stuff. So you can see that at level 0, where we start, is the root node. Then there are two childs to it, B and C, which can be called as siblings, and child to them are the parent nodes. Child to them will be D, E, F, G, and B and C will be called them will be called as the parent nodes to them. You can also see the example of the child in image, which are H and I, and the relationships or the connections are set up with the nodes are called edges. And last are the leaf nodes. Leaf nodes are nothing but the nodes which does not have a child. So the number of children a node may parent depends on the type of tree, which a tree is branching factor. So which dictates how fast the tree will branch out as nodes are inserted. So let's just discuss some of the applications of the trees, starting with the Huffman coding used for data compression. Uh, it's uh, it uses a binary tree that determines the best way to assign codes to symbols in the data. If symbols are frequently occurring, and they are assigned short codes and longer codes if less frequent. Then the user interface, the Windows take on a hierarchical arrangement, forming a tree, except for the root window from where the parent has started, and each window may have several child window. Directories in hierarchical files systems also have some such a similar organization to it. Then the database systems, in, in particular those that require both the efficient sequential and random access while performing frequent insertions and deletions. So the binary tree categorized generally as a balanced search tree with a large branching factor is especially good in this situation, which is optimized so that the disk input output is minimized when accessing the records in the database. The next is expression processing, a task performed frequently by compilers and handheld calculators. So one intuitive way to process arithmetic expression is with an expression tree, a binary tree containing a hierarchical arrangement of an expressions operators and operands. So you can see the example of expression processing in the image for the given expression. So, so the expression being divided by the uh, terms in the parentheses and and the multiplication. So, moving on forward with the example 5, which is for artificial intelligence. So it is used for making different kind of decisions in AI. So it's a discipline that addresses many problems traditionally difficult for computers, such as logic-based games like chess. So many AI uh, problems are solved using decision trees. The decision tree represents different states of the problem and what decisions to make to continue to reach to a conclusion. Next is event schedulers. So often real-time systems require looking up and retrieving the latest information associated with the events as they are triggered. Then priority queues, so data structures that use a binary tree to keep track of which element is set as the next highest order. So basically, we are not needed to sort the elements in particular manner, but rather have a priority to it. So next is the description of the binary trees. So apart from the children and a parent, nodes can have siblings, descendants, and ancestors. The descendants of a node are all the nodes branching out below it. The ancestors of the nodes are all the nodes along the path between it and the root. Then the evaluation of the binary tree, how are basically the binary trees are evaluated. So the performance of the tree is often discussed in terms of height, which is the level of number of levels that we saw in this image. We had level 0 through 4. And each node is in a binary tree contains 3 parts, which is a data member and a pointer, 2 pointers, which are left and right pointers. So using 3-member structure, uh, we we form a setting for a child node with right and left pointers. If we do not have it, then we can assign a null value to it for the appropriate pointer, which also marks the end of the branch. Then a leaf node is a node which does not have any children. Then a collection of tree structures being worked with together are called a forest. So you can see the two examples of the trees. First is for the tree terminologies, uh, for the parents, for the ancestors, for the children, then leaf nodes, the descendants of node 67, then particularly only for this image, then for the siblings, then the branches and stuff, and also marking of the root node 44. Then coming to the image B, it uh, represents a representation of a node with the right and left pointers we just discussed with its data member. So moving forward, so after discussing about the trees, we have to state a specific way in which we have to traverse it or travel each and every node. So this is what the traversal method does. So tree traversal is a systematic process of visiting and examining each node within a tree data structure exactly once in a specific order. So typically there are pre-order, in-order, post-order, and level order. So starting with the pre-order, we traverse the root node first, then left node, and then to the right. Similar method for a subtree. Then a subtree is nothing but a smaller tree contained within a larger tree. So, so this is also known as a depth first exploration way. And then moving on to in order. So for a given subtree, we first traverse to the left, then to the root, and then to the right. Um, and similar pattern for traversing a new subtree. Then to the post order traversal. For a given subtree, we first traverse to the left, then to the right, and then to the root. In the level order, we visit the nodes beginning at the root and then proceed downward, visiting the nodes at each level from left to right. The level order traversal is the breadth first exploration. So now let's see some visual example of these traversal methods. So you can see the order for starting with A, you can see the order in which the pre-order traverses a tree. Then starting with the root node, it goes to the left, then to the right. In in B, uh, it goes to the root, then goes towards the right. Then in post order, it starts with the left node and uh, goes to the root node at the end of it. Then in image D, which is for level order or breadth first exploration, all the levels first of the tree, all the levels of the trees are first traversed, and then later on they are, uh, and in the end, they are reached at the end of the branch. So next is tree balancing. So why do we balance a tree, or what is the need of it? So balancing a tree is a process of keeping it as short as possible for a given number of nodes. This means that making sure that one level of the tree is completely full before allowing a node to exist at the next level. So the reason to do it is for the optimized performance. So a balanced tree ensures that the tree's height remains relatively low compared to the number of nodes, which can lead to more efficient operations such as searching, insertion, and deletion, which can contribute to the optimal performance. So in the image down, you can see that the left balanced binary tree. Next is the implementation and analysis of tree. Uh, so these are the structures that we are going to form in the program, and these will be used uh, uh, in uh, for the further implementation as well. So first, starting with the by tree node, which is binary tree node. So which will be having three members as discussed before: the data member, the left and right pointer. Then for the binary tree, there will be four members, which will be size, which tells us the number of nodes in the tree. Compare, which will be discussed in different session, but it is then it will be then third is destroy to encapsulate the destroy function passed by the bytree init. So bytree init is nothing but an initialization to the binary tree function. So within that, we'll be passing a destroy function. And then a root is a pointer to the top of the node hierarchy. So, so before starting the discussion of it, the only operations right now we'll be discussing within for the program will be the inserting and removal of the nodes at the leaf nodes only. Uh, so the insertion and removal operations will be only on the leaf nodes. So starting with the binary tree init, as mentioned, it initializes the binary tree, and a destroy function is passed to deallocate the memory which was allocated to it. Then binary destroy for destroying the whole binary tree specified by the tree. Then binary insert left. It inserts a node at the left child of the node in the binary tree specified by the tree. If node already has a child or left child, then it will return -1 as the value. And if the node is null, the new node is inserted as the root node, and that what it's mean. If the node is null, it means that there are no nodes. So that is it. So it will insert a new root node. So the tree must have uh, tree must be empty to insert a node as the root node. So otherwise it will return -1. Next, we have a binary tree insert right, which is similar to the binary tree insert left. It inserts the child at the right of the node specified by the tree. Then binary tree remove left, which removes the subtree rooted at the left child of the node from the binary tree specified by the tree in the init. And then if a node is null, all the nodes in the tree are removed. Same is for binary tree remove left right. So this operation is similar to the binary tree remove left, except for it removes the subtree rooted at the right child of node from the binary tree specified. Then a binary tree merge, which merges two binary trees specified by the left and right to the single binary tree in called merge. So after merging is complete, merge contains data in its root node, and left and right are the uh, le left and right subtrees of its roots. So once the trees have been merged, left and right are as if bytree destroy has been called on them. So basically, we are resetting them to 0 for unintended use of it. Then bytree size for which is a macro which evaluates the size of the tree. Then bytree root, which gives back the value of root on the tree of the tree. Then by tree is end of branch, which specifies whether it marks the end of the branch in a binary tree. Then by tree is leaf macro that determines whether the node specified as node is a leaf in a binary tree. Then by tree data, which gives back the data stored in the node. Then by tree left, so a macro that evaluates to the node of a binary tree that is the left child of the node specified by the node. So similar to that, it's a by tree left, which evaluates the node of a binary tree that is the right child of the node specified by the node. So after discussing uh, some of the controls from the surface level, uh, let's discuss a bit more in into the workings of how they work in deep. So a binary tree insert left, it inserts a node in the binary tree as the left child of the specified node. The call sets the new node to point to the data passed by the caller. Then linking the new node into the tree is accomplished by setting the left pointer of node to point to the new node. If the node is null and the tree is empty, we set the root member of the tree data structure to the new node. We update the size of the tree by incrementing the size member. Then binary insert left. So binary tree insert right operation inserts the node in a binary tree as the right child of a specified node. So similar to the binary tree insert left, the node uh, new node into the tree is accomplished by setting the right pointer of the node to point to the new node. Then binary tree remove left will remove the subtree rooted at the left child of the specified node. Then nodes are removed by performing a post-order traversal beginning at the left of the node. Then in the end, binary tree merge, it merges two binary trees in single binary tree called merge. So because it merges in a tree called merge, we first have to initialize the merge by calling the binary tree initialization on merge. So after that, we insert the data into the merge tree at its root. The merged trees left and right children are then set to be the root nodes of left and right, and the size of the tree is adjusted to reflect the size of the subtrees. Last, we detach the nodes now in the merged trees from the original trees and set the size of each tree to 0. So this is basically done in order to not have an unintended calculation affect uh, the actual tree or the original tree or the merged subtree or the tree. So starting with the .h file for the program. First are the header. First is the header file. Then we define the structure of the by tree node. As you remember that it has three parts, which is the data member, and then the left and the right pointer to it. And by tree node is the element. Then next we define the structure of the tree. Remember that it had the size of the tree. Compare is not the operator. Compare is not something that we will be discussing for this session. Then uh, destroy and the root, giving us the root to the tree. And by tree is the member to it. Next are the initialization operation for the tree, the deallocation of it, then inserting the value at left, inserting at right, then removing the left, then removing the left, right subtrees, then merging of the trees that we just discussed before this, taking the arguments. These merge is a tree that in which the both the left and the right part of the trees are going to be merged and stored into. Next is the size of the tree, the root of the tree, uh, checking whether it is the end of the branch or not, the leaf, the data, then uh, uh, knowing about the left and the right of the tree, node of the tree. So these are the basic structures that uh, of which the components we discussed in the slides. These are these are how they will be implemented in a program, or let's say just have a separate file for them to be called whenever we want to use them for whatever reasons. So next is the actual .c file. We have our needed header files here, including the bytree.h that we just discussed. Then first we initialize the tree with the needed values, or the initialized values. Then we discuss about the destroy function of the tree. First, so here, apart from the destroy function, this is done as a precautionary measure for preventing any data leaks or something. Then we have the binary tree insert left, or inserting the node at the left of it. First, we check where. First, we check whether the node is not null. Uh, if it is null, then it means it's a root node, and it inserts it at the root node. If the if if we actually have the first we do it for the root node. If we actually have the node or the space to be inserted, then we insert at the left node. We first do it by first allocating the size of allocating the space, then inserting the node into the tree. And then because of insertion, we adjust the size of the tree, and uh, it will return 0 for the successful insertion. Next is the insertion at right. So it's similar to the one that we have saw for that we just saw for the left. It is done for the right. Similar conditions have been checked for root. Then uh, if it's not at the root, then for the end of the branch. As you remember that this program we are discussing is only the insertion and removal operations are only done at the leaf nodes. So similar to the left one, inserting the node into the trees, then adjusting the size of the tree. Next is removing the node at left, or leaf nodes at left. First, checking whether the tree is not empty or not. Then determining the node to be removed, removing the nodes, and also remember that destroy function is a user-defined destroy function. So we'll be deallocating the memory and adjusting the size of the tree. Next is uh, By binary, just a second. So next is binary trees remove next operation. First we check. First we call it, and then we check whether the tree is empty or not. Then we determine the node to be removed, and we actually remove the node. We use the destroy function and also free the position pointer that is pointing to uh, the tree here. So uh, assigning it to null and adjusting the size of the tree. Next is the merge operation that we discussed, which is merging of two subtrees with their root nodes. So first we initialize the tree with the same destroy function used for binary left. Then then we insert the root node as mentioned here. Then so merging the two trees for left and for right, both of them. Then adjusting the size of the or calculating the size of the whole tree that we just formed, and deallocating. Remember that we reset the value of left and right to 0, because these left and right are actually pointing to the original tree that they pointed to. So for the unintended use or miscalculations or any kind of maneuver, we will equate it to or reset it to 0 uh, for its unintended use within the program. So this was for the merge. So yeah, this was a simple and introductory presentation for the binary tree, where we discussed some of the simple operations regarding the binary tree, uh, and we discussed it with it within the constraint of uh, having the insertion and deletion only happening at the leaf node. So yeah, this was it for this presentation, and thanks a lot. Thanks a lot for listening.
Jamit, good. So binary tree is what the coverage was. Binary tree and binary tree in terms of only child two childs, and that is you have a branch and you have a level, right? So you have only two. If we go to three at the level, every level, or let's say, then it will be more than two, right?
Yeah,
So
it will
right
have
now we have only
the
two branches. We
yeah
can have 3 branches, 4 branches, n branches. So the complexity increases, but at the same time the depth, the number of levels decreases if you can spread it across. So you had also discussed about the what you call depth first and the breadth first. Depth
yeah
first is you are going down the tree, left,
yeah
whereas you are going towards the branches if you are going breadth first. So there are the terminologies are little confusing, but you once you go over it, what is depth first, what is breadth first, and what is the search mechanism, you will Probably you'll have to run over the record and maybe look at the mm, slides and again to be able to get it. Anybody has any question? Go ahead. Ask Jamie. Thank you. Kunal, Ramesh, or Saroj, or Amol, anybody? Any questions?
No, currently.
No, Prakash.
Okay. So what I'll do is we'll just post this uh, in the YouTube as usual. We have all the recordings available to you. In the chat window, I have put down the uh, so there, Amol, there is no GitHub repo for this. We are not maintaining GitHub repo, but what we have is a Google Drive or something, and this is the link for the what you call the YouTube recording. And those who want to have access to Google Drive, please give me the what you call your email ID, or you send what you call uh, to info at eotf.in, the mail I am leaving. If you send me the yeah, okay, I got it. Amol, I got. If anybody wants to send it privately, you can send to eotf.in. And what I will do, you can or either put it here, and I'll make sure that you have the uh, Google Drive access where we have the PowerPoint presentations available. So the PowerPoint and the code is available in public, and that Jamit can refer. Jamit, you can if you have the link to the code, can
Uh,
you put it so that they can download the code? You can. So the way it works is like you have a code, entire code with the book. The book name is, as you know, the recommended book is Mastering Algorithm with C. And this is a O'Reilly publication, and it is by Kyle Luda. And this is a publicly available code which can be downloaded, and there are multiple versions. One version is the what you call the Windows version, which can be Jamie, which showed he's using Windows 10 to do that, whereas the other version is Linux version. So if you have a Ubuntu or something, you can download the tar.gz file. If you are a Windows, then you can use the zip file. Once you undo, that is you unzip, or then you can get the entire code. So Jamie has put out the code list. You can go to the code, download on your uh, machine, whichever you prefer, and then you can set up your make file, or once you have the what you call algorithm top level directory, if you put it in your path, then you will be able to execute each of the code directly as a make file. There are exercise 1 and 2 per say per chapter in the book. So since we have been covering religiously following the book as our guideline for presenting as well as for execution, it will be easy for you to go through each of the code, check for yourself, and that's the best way to learn, provided you don't have to really know full C. A GNU C is enough. So if you take any Linux default or any Charm, PyCharm, not PyCharm, what is the which one you are using compiler?
uh,
C98, GNUC, right? GCC. Yeah,
yeah,
Ming WC, I
yeah,
think.
I am in
So
GW.
Ming GW, yeah. So Ming GW is nothing but Ming has it's a compiler for C, uh, a version of GNU-C in Windows. And all these are open source, so you can download and you can execute on your own, try it out. If you think something uh, is needs Q&A, we'll have a Q&A session next time with our own questions fielded from the book, so that you once you go through that, you will understand how to conquer the beast. Data structure and algorithm is complex, even though in terms of logic it is simple, but in terms of algorithm execution, being able to use it from different languages is important. So we have chosen C because we started with C. If you do a wrapper around using Py, you can use it with Py also. Py can call a C. So these live codes you can use in your practice also to learn and to be able to understand the concept. And so this is at the very what you call code level. You can understand at the diagram level. You can understand the concept level. You can, because we always have a data structure defined. What is the structure used for it, and how the structures have interfaces to do the operation, what are the various operations, and how it is applied, and how you can reduce the complexity, how you can improve the efficiency and all that. Hopefully, and this does not require any GPU type stuff because you are only experimenting, and so a simple notebook can take care of this. So even a Windows 10 or a Ubuntu or any of the Linux boxes can take care of this. So simple home computer or a desktop computer should be able to exercise the codes on this. So hopefully you can revive your most of you, if you have already, then you can remind yourself and be able to use the concept in works, and otherwise you do have a initiation and you can go through the entire. So all codes are available. Every book is book recommendation is there, and we follow religiously. Anything from outside we bring is only to enhance the understanding of it. Okay, so that is all we have. And Amal, thanks for the support, and all of you can join next week again. Not next week, this is today's Friday, right? So Jaimit, are we going to have any session on Saturday?
No, not.
Not this Saturday.
No.
Okay, so we'll be doing Monday then, right?
Yeah.
So Monday evening again, look back. We'll see you all at 8 p.m. Okay, and go through the YouTube exercise. Everything is posted. This one I'll post it in another half an hour or so. Okay, thank you, everyone.
Okay. Thank you.
Yeah, we'll end the call today. Thanks.